Hey there, in this video we're looking at C++ Interlude 8 in the Walls and Mirrors data structures text. And this one's about the standard template library in C++, or the STL as a lot of us call it. So this is going to mark the end of our course in data structures. And this gives us, on the one hand, it gives us a summary of everything we've talked about all semester long. And on the other hand, it gives us a look at all of the options provided in the full C++ STL. So let's take a look at this. The C++ standard template library, and this is an add-on library that is conventional in any kind of C++ package nowadays, provides you with a library of container classes like the ones that we've developed in this semester of our course. So all of the stuff, all the data structures that we talked about, the bag, the stack, the queue, the list, the priority list, all that kind of stuff is provided in the C++ standard language nowadays in the STL. So very convenient that all these standard things, these standard options in which you can store data are provided that way. They are templated classes, so you can store any type of data, any type of objects in them. They're really normal things that you would expect to have available in any kind of programming environment. So they are all just available to you in the STL. Side point, when I started with C++, this was not available actually. So this was an add-on that started in the 1990s, I believe. And so this is a customary thing that you expect to have available to you when you need a stack or a list or a queue or something like that. So one question we might pose is, why did we do that? Why did we spend a semester of our education developing our own abstract data types when they're just freely available in the STL in the first place? Well, there's a bunch of reasons why I feel that it's important that we really understand fully how these things work by building them ourselves. So item number one, we've learned how to develop abstract data types on our own, maybe for things that aren't in the STL. First one that comes to mind, trees. The tree data type is not in the STL, basically because the way that it branches and it has a whole bunch of options for things that we might do. Our textbook here, if we dig into the specifics, has a whole bunch of options for different ways that you can set up trees. They could be binary trees, they could be 2-3 trees, they could have more branches, they could have less. And the multiple variant number of branches is actually not something that you could conveniently do through templating. So that's just one example with the trees actually. But there are other more sophisticated, maybe more exotic abstract data types that someday you might need to manage or build yourself that aren't in the STL. So you've gotten some practice with the issues around building data structures. Number two, you might be working in a project where they disallow the STL. So some workplaces and some projects want to take closer control over the data storage for particular reasons, and they might not use the STL. They might not permit you to use the STL. So having familiarity with different ways that things could be structured, and being accustomed to, sometimes you got to dig into the specifics and maybe change them, and you have some practice at that. Three, more generally, we want you to have a general perspective about the issues of data structures. So we've been working in C++, but we want you to be able to work in other languages as well. So if you move to the Java language, or you move to C# or Python or something else, or maybe languages that haven't even been invented yet, we want you to have the general idea about what data structures you should expect to have available. They might have different names, possibly, that you'll have to look up. They might be slightly different structured, but the basic ideas should be consistent, and you should be able to transition to another language pretty conveniently, pretty efficiently, if you have the broader idea of how data structures are going to work and what ought to be available to you. Some other things I can think of, I feel like it was probably good for our discussion of complexity, of what data structures are more or less efficient. that we could dig into concrete examples and really explain why one is more efficient than the other. So for example, accessing one particular thing somewhere in an array is big O of 1 complexity, very efficient. Getting to any particular thing in a linked list is big O of n, because you're going to have to traverse from the start all the way through to find the thing that you want. So array, great. Linked list, not so great. On the other hand, inserting an item somewhere in the middle of an array is big O of n, pretty slow. Whereas doing that with a linked list, assuming you have an iterator to the right place, is big O of 1, basically instantaneous. So inserting something at the start or in the middle of a linked list, very good. In an array, very bad. And so as we started to educate ourselves about those issues, I think it's handy to actually have the concrete specifics so we can dig into about why that's the case, instead of just like memorizing it as facts that are delivered to us. So I think that's the point of a standard data structures course in your computer science education, and I'm glad that we were able to spend some time on those details actually. Okay, so talking about the STL, the way that they provide and have developed these standardized containers, there's 3 major categories of them. Number 1, sequence containers, where it makes sense to track the items by an index, like an array. So sequence containers are things where it makes sense to ask, give me the 3rd one, give me the 12th one. So that's the kind of thing that makes sense for an array or a list. It would not make sense for a bag. A bag is supposed to be just a bunch of stuff and you don't care about the ordering of it. So for things where you don't care about the indexing or the ordering, that category is referred to as an associative container. It's a bunch of stuff that has some kind of association to it, but you don't track them by index. Instead, you track them by the value, by the key values. So with our bag ADT, the only thing you could do is just look up and say, is this value in the bag? Yes or no. That's actually all you could do with it. And that's equivalent, I guess we'll see another example here, to a mathematical set, right? If you're dealing with a mathematical set, it doesn't make any sense to ask for the 3rd one, because a mathematical set isn't supposed to care about the order. And they're also not supposed to care about duplicates, things like that. So that makes it an associative container. And then 3rd, you have what are called container adapters that are restrictions, or I kind of want to say an overlay of some particular ADT interface on top of another way of actually literally storing the data internally. So an example of that is you want stack behavior. Okay, so we can give you a stack, but then there's a separate issue about how did you actually store it? Did you store it internally as an array, or did you store it as a linked chain? So the container adapters are, in some sense, this cover over another data structure that you could possibly swap in or out. So we're going to go through the different options available in these different categories on these next couple slides, largely so that you're familiar with the names of them. The names might be different in the C++ STL versus the ones that we've used in this course, in this textbook. So this will make you familiar with the STL names, and then at that point you can look them up. You can, on the day when you need them, you can do an internet search for them. You can look up the details in our book if you want to. And for what it's worth, our book has all of the primary functions that you would use for these different ADTs, and also the big O complexity for each of these functions, so you can compare and contrast and pick the data structure that is most efficient for the job you're trying to do. Okay, so we're not going to go through all of that in this video, but the main thing is you'll know the names, you'll know what to look up as far as your menu of options. The other thing I'll say is in this video, the list that we have here, I'm pretty sure is complete for C++ 11, but the C++ committee has been adding new ADTs to the STL since C++ 20, so there are new ones that are going to be added over time to keep C++ kind of on the bleeding edge. But this list here are the ones that were introduced as of C++11. So let's start taking a look at that. Okay, so first of all, sequence containers. Again, ones that make sense to think about them like it's a sequential list with some kind of order to them. So first of all, there is a class called array. Again, an actual object class in the STL called array. It's a templated class, so you can store any type of thing in it. So that provides functionality like a fixed size array. Okay, so like a raw array in C++ or C other languages, but with a couple extra features, the most notable one with range checking. So when you try to access something in this object class, they make it look like it's an array, but when you try to access, there's a specific function called at, I believe. If you try to access something past the end of the array with at, instead of a buffer overflow, it just throws an exception and prevents that. So instead of some kind of weird, random, corrupting, anything could happen error, it just stops you. So that makes a lot of sense. And the fact that the array class is in the class hierarchy with all these other classes we're looking at means it works with the STL algorithm functions efficiently, and it works polymorphically and all this kind of stuff. So it's convenient to have an object type in the same class hierarchy as this. And so you might consider, some people say, why use raw arrays anymore? Why not use the STL array class? And it works like other stuff and it's a little bit safer, so that could be an option there. Second, we have the vector. Hopefully you've seen that a lot in the past. Vector, and a lot of people, they use that now as their default storage. If they're kind of not thinking about it and nothing else presents itself as important, by default, use a vector. I guess that's a good starting point. And of course, the vector is what we call formally a dynamic array. It's really an array internally that can grow and shrink in size. And maybe once or even twice, we've seen how that actually works. Is it dynamically declares the array internally, and when you store too much stuff in it, it dynamically allocates a double size array, is what C++ does, and then deletes the original one and just points the internal pointer at the new array. Okay, now other stuff, there's a class called a deque. And a deque represents a double-ended queue. So the main idea is you can add or take away stuff from the front or the end is the primary expectation for that. That's actually stored internally, kind of an interesting strategy, as a group of linked arrays. So you can add stuff, and then if you need to insert stuff, they actually have pointers that link you to a newly allocated array. So, internally, that's a little bit complicated because it really has a pointer to an array of pointers, and the pointers are to the arrays with the actual data. Obviously, you don't need to deal with any of that complication when you use a deque, because externally it just looks like a double-ended queue like we've talked about in this course. The reason why they set it up internally like that very intelligently is that it avoids recopying new items when you have to insert stuff. So with a vector, if you insert stuff in the middle, you got to move everything one space down. You have to copy all that stuff, which is a big O of N operation. But with the deque, if you have to insert stuff, they can just make a new array and just link the pointers to it, front and back. So that could possibly be a big O of 1 operation, be much more efficient than the main problem with an array or a vector of when you need to insert stuff at the beginning or the middle. So the deque makes that better. Clever. Okay, there is a class just called list, which by default is a doubly linked list. And I think we've seen a couple times that it is efficient to have a doubly linked list, be able to move both forwards and backwards in your list, and it cleans up some of the traversal code when you do need to insert stuff or delete things or stuff like that. So by default, if you ask for a list in the STL, it's doubly linked. Great. I think later on they added the forward list type, which is a singly linked list, which is actually the first thing we saw in our course about lists. So that's not normally the first option people go for. But if you were worried about the extra memory that you're using up with the 2 pointers per node, instead of the one pointer with a singly linked list, you could ask for a forward list, save a little bit of memory. Most of the time, it doesn't make too much difference. But you would also want to check in and go, for my use of this, I only go forward. I never go back. I only go forward through the list. Then that would be an option. I don't use that a lot, but it is an option. Okay, that's all the sequence containers. As of C++11, there's only 5. So there's your options for things when you're going to want to ask for one thing back by index. Right? You can do that with all this stuff. Okay, so associative containers, there's no indexing. So they're just holding a bunch of stuff, and you have to ask for things back by value, a lot like our bag. So 4 things here as of C++11. There's a set, and maybe we've talked about that in our course, just like a mathematical set, exactly the same as that. You store a bunch of stuff with unique values. You can't store 2 copies of the same thing. Just like a mathematical set. If I have a set that's ABC and someone says they have another set that's ABCCCC, those are the same set. Having duplicates in a set doesn't make sense mathematically. So just one copy of each of the things, that's a set. If you allow multiple things in your collection, but you don't care about the ordering, mathematically, we normally call that a multiset. So a multiset is like a set, but you can store copies, multiple copies of particular values. Now, in our course, we called that a bag. And in some circles, in some places in computer science or applications, that will be called a bag. But in the broader world, we normally call that a multiset. And in a mathematical text, that would be a multiset. If you want to look this up on Wikipedia, you're going to be looking for the multiset article. And then it says, oh, some people call this a bag. So exactly like our bag that we started with in chapter 1 of this course, the STL called that a multiset, which is actually the more common thing nowadays. Okay, now there's a data structure called a map, which stores data as a group of pairs, where you have a key value, which is the thing that you're going to search for, and then the value, which is actually the data. And with a map, those have to be unique like a set. So the first example that comes to mind would be like a customer ID. That would be your key. And then all the things in the customer record is like name, address, phone number, credit card, stuff like that. That would be the value of that data. So for a lot of record keeping systems like that, an ID number, it could be like a social security number. There's only one of them in the system. You can't have 2 people using the same customer ID. So that kind of storage mechanism would be called a map. And you're always, when you're searching for something, you're always searching for the ID number, basically. That's in the Walls and Mirrors textbook. We may not have had time to get to it in our course this semester. Again, a variant name there, the Walls and Mirrors textbook calls that a dictionary. So if you look in chapter 18, you're going to see a full coverage of how to define and how to implement the dictionary IDET is what they call that. But in the broader world, at least the STL called that a map. So map is another word for a dictionary here. So that's what the STL called it. And again, the map only stores unique keys, just one version each. If you're in a situation where multiple data records could possibly have the same key, that would be called a multimap. So like a map stores pairs, a key and a value, but for a multimap, you can have multiple things with the same key. So 4 associative containers built into the STL here. Now, everything on this page, for what it's worth, a little talk under the hood here, everything on this page is implemented as a red-black tree. So a red-black tree is a specially constructed binary search tree to make these kinds of containers efficient. And if you want to see the details and the information about how to make a red-black tree, that's in chapter 19 of the Walls and Mirrors text. Now, everything on this slide here is technically stored in a sorted fashion. And you can see that like with the set at the top here. It says store a sorted group of unique values. So internally, the red-black tree stores things like it's prepared to be sorted, like in a binary search tree. So if you have a set, and you store, let's say, the characters X, Y, Z, A, B, C, and you iterate over it, it's actually been stored. You get them back in order A, B, C, X, Y, Z like that. So that's happening internally. If you iterate them, you actually get them in order. You know, that maybe that's handy. The red-black tree does that automatically for you. Now, all 4 of those associative containers have a variant that's referred to in the STL as an unordered associative container. So all that stuff has an unordered version where they drop that whole sorting issue. So there's 4 classes here. There's unordered set, unordered map, unordered multiset, unordered multimap. So they are not saved internally in a way that they're inherently sorted. They drop that red-black tree implementation and use an entirely different way of storing the data that's called a hash table. And the advantage of a hash table is that whereas searching for something in a tree is big O of log n for a, pretty efficient for a balanced tree, well, with a hash table, access time is always instantaneous. It's big O of 1. So you can immediately jump to the thing that you want in a hash table effectively instantaneously, which is wonderful. The disadvantages are, in order to set that up, you need to make a math function, a special math function called the hash function, and you're going to have to kind of dig into the mathematics of an efficient hash function when you use one of those things, and they might possibly use a little bit more memory. You'll have to get a block of memory, and you might not use all the spaces for your hash table. So, as usual, pros and cons. There's an advantage and a disadvantage. If you don't care about the sorting and you really need faster access time to individual things, a hash table is probably better, actually. You want to see the details of that? That's in our book, chapter 18, section 4, 18.4 there. Hashes are very important. You should probably know about that, actually. All right, and then third, there's the container adapter category. And again, these are interfaces, really overlays of some kind of behavior that you want that we're going to plaster on top of another data structure, really. And there's 3 here. So exactly like we have discussed in our course here, everybody's got to know about these. There's a stack container adapter, just like we've talked about in our course. There's a queue, and there's a priority queue. Makes sense, they got to be there in the STL. Now, by default, the stack and the queue are actually stored internally as a deque, right? That, like we talked about a couple of slides ago, the very intelligent, smart way of it kind of works like a double-ended queue. It's really a bunch of arrays. When you need to insert, you don't move stuff around. You just plaster in a new array, actually, in the deque. So that's the default for stacks and queues. On the other hand, the priority queue by default uses a vector. What makes sense for that. But the programmer, if you want to really store the data in a different internal container, you can ask for a different container. So if I just ask for a stack in the STL, it's really stored in a deque. But I could ask for a stack template vector, and then the data is really stored in that container. So anything that we talked about could be used as the underlying storage for any of your container adapters. If you realize that for efficiency of purposes, one of the other ones would be better. So that's kind of a neat little feature. All right, so again, so that's it. That's all of the container classes in the STL as of C++ 11, actually. So that's what most of us think about as our menu of options for how you can store data when you're using the STL. Now, you can dig into the walls and mirrors text for more detail on all of these things. So the textbook in this particular interlude walks through all these different containers, gives you a list of the primary functions that you would be using for all these things, and then also specifies the big O complexity so you're aware about operations that are more efficient versus take more time. So we're not going to do that here, but let me just give you an example of one of those tables. The first one in the interlude in the book there is, well, here's operations that we expect in all the containers. So here's just like a beginning of learning about the STL. So obviously every container is going to have a constructor that creates the container, obviously, usually of a specific size to begin with. The efficiency of that varies. Okay, so for an array, super simple. If you're doing something more complicated than that and laying out multiple nodes, maybe when you get started, that's going to take more time. Okay, that's not too surprising. There's got to be a destructor, no doubt about that, that cleans up, deletes all the memory, hands it back to the operating system, make sure there aren't any memory leaks, right? The STL has been tested to be bulletproof on that particular aspect. So going through all of the items, the efficiency there that you would expect would be big O of n. So for a linked list, obviously you have to go through all the things that currently exist and just get rid of all of them. So that would be big O of n. There's going to be an assignment operator. Every single one of these containers, like we talked about in a prior interlude, we would expect to overload the assignment operator, the equal sign, to make a deep copy. So that assigns all the entries on the right-hand container and sets the container on the left to be containing a copy of all of that stuff and only all of that stuff. So making a deep copy there would be a big O of n operation because it has to go through all the things one at a time and make a new version of it. Every single container has an empty function that returns true or false whether or not the container is empty, which is to say has size 0. We guarantee that is big O of 1 for all, so basically instantaneous for all those containers. That's a very fundamental operation that if it wasn't obvious already, the work has been done in to make sure that that's perfectly efficient. And then there's going to be a size function that returns how many things are in the container. And again, that is guaranteed to be big O of 1. That, for what it's worth, that's set up to return an unsigned integer because you can't have negative size on a number of things, obviously. And, just thinking about the big O of 1, if we look at the version of the linked list that we saw prior semester, when we made a size function for that, it just traversed the whole list. And every time you called size, counted up everything in the list until it ran into the null pointer. So if you do it that way, that would have been big O of n, and it would be repeating the count every time. But in this course, this semester in this book, we separately kept on to a item count for our linked list, specifically so that whenever you ask for it, we can just serve up the count immediately and have it be efficient in big O of 1. So that is what all of the STL containers guarantee is going to happen. If you need to call size a bunch of time, you're not recreating the count all the time. And I'm glad they set it up that way. Okay, so again, you can look at the other functions in all the individual containers there and kind of be aware about what functions would take more time if you had to do that a bunch. And maybe there's another container that makes that same operation more efficient. And you can see all that in the book. One quick example just to see what using the STL would look like. So if we want to use a stack from the STL, you just have to include the stack header file. So usually all these different containers have their own header file like that, you could guess. And it is templated. So what we would do here, for example, is we just declare a stack events. Going to call that a stack. What they're doing here is they're testing all the main functions like we normally do in our test driver. So you can check out that empty function and confirm that's working properly. Again, that'll be part of every single container. That's a very basic thing here. And then they're going to push some data in. Going to push 5 things in with the push function on a stack. And then we're going to get everything back out with the strategy of using a while loop. And as long as the stack is not empty, get the top, print it to the screen, pop it, move on to the next thing, and then you'll be done. So as you can see here, the stack class has a push function, has a pop function, has an empty function like everything else. And that's how you could very quickly use a stack. Hopefully that looks familiar to you. The STL is set up the way that it ought to be, basically. and a stack is available to you when you need one. Now, the other thing I'll just point out is that, again, the underlying data structure here, as we said, is a deque. So if you didn't like that, on this very first line, the main function here, you could write stack angle bracket int comma some other type, like vector event or Q event, I suppose, or set event. I think that would probably work. Probably that would work. Maybe. Maybe it needs to be a list type container. But anyway, so there's a couple of examples there if you wanted to use a different underlying structure. But this works perfectly fine. Most of the time, you don't even have to worry about that. The deque is a good choice. So just give me a stack and it does the job for you. Wonderful. Okay, and then on the other hand, the STL, we probably said this a couple times, has an algorithm library of a bunch of functions that you commonly do, and we've probably done a number of times with your data containers. So for any of these things, you would include the algorithm header file, and then you have access to the built-in STL functions of find a particular thing, do a search, do a linear search on my container, or count how many times this thing shows up, kind of like we had in our bag at the start of the course, or sort the things, put them in a sorted order if they aren't already, or copy some things, or find the smallest element in your container, or find the maximum, the biggest element in your container. So a bunch of stuff like that that the STL will just automatically provide for you. Now, all of these things work using iterators. So the STL containers all have iterators made for them. And they're all the iterative ones are going to have a begin function and an end function to get an iterator, the beginning and the ending. And most of these functions, as we saw in the prior interlude, are like the find function takes 3 arguments. It takes an iterator, the beginning of your container, an iterator marking the end, and then the actual data item that you're trying to find in the container. So in order to use these things, you do have to know about iterators. If you missed it before, that was the prior video to this one. You should find out about iterators. And that is how all these functions are set up for you to use when you use the STL. Super convenient. All right, so you're just starting out learning, about the broader world of data structures and specifically STL in this particular video. So on the day when you need to make a decision about what data structure to use in your project, and this is kind of one of the really important high-level decisions that you make when you're architecting a larger project. The decision should be made hopefully up front, get the requirements, make a good decision about what kinds of tasks you need to do more versus less, pick the data structure that's efficient for that. Usually my first resource, you could use the textbook here. You could use the Walls and Mirrors textbook with the last interlude on the STL. It's a great resource. You could also look for places online that have this kind of information. Wikipedia is a great resource. There's a main article on STL containers of what your menu of options are. They keep that updated as new containers are added since C++20 and later. And there's a separate article on each separate type of STL container. So you can go there and you can get the main idea. What's the purpose of this? What's it basically good at? What is it not efficient at? So frequently I go there for when I need to brush up or a first overview of a particular container type. There's also the C++ reference site that I use frequently when I'm teaching my classes. That's at cppreference.com is where that is. And that has full, complete, sometimes brutally complete details on all the containers and all the algorithms in the C++ standard library. So when you need to use one of these things or any particular function, there'll be a specific page about exactly what all the arguments are and what the return value is, and some talk about complexity, about how efficient it is, and there'll be an example of using this particular function or this particular container. So that is, as of this writing, that is a really great reference, frankly, and I go there when I need full details about what I need to use in C++, frankly. So I should have on the description to this video, I should have links to both of these resources here. So when I'm researching some particular data structure at one of these sites, I usually discover some interesting new detail that I didn't know before, or an option or a feature, or maybe like a brand new container that's been added to the STL that I'm personally excited to try out for the first time. And I kind of hope that you have that same experience when you are looking stuff up in the future yourself. And I hope that in general, this semester has given you a good foundation for selecting and using the right data structures and being able to explain why to somebody else when you need them for your projects in the future. And with that, we have reached the end of our course in data structures. Bye for now.